Hello, my name is Ignasi. I'm the lead data scientist at the Security Operations Center at Nestlé, and today we're going to see how we're using deep learning and image recognition to fight phishing. Together with myself, Fran from Plain Concepts, who is a machine learning engineer that also participated in the development of the product, will also jump in briefly to explain you part of it. Okay? The agenda that we'll follow today is as follows. I will start with a brief introduction on Nestlé, even though probably you all heard of it. And I will go up to the Security Operations Center, which is the group where I actually work and where we fight with this kind of cyber threats. After that, we'll see very briefly how the solution looks like. How do we actually tackle phishing with image recognition? And after that, Fran will jump in with the architecture and will show you how it's built on the back end behind the scenes. After that, I will go back into the presentation and walk you through all the initial attempts that we had with the solution and all the lessons that we learned. And finally, I will show you what would be the final product that is currently in production. We'll see some real examples as well as some performance metrics, and finally we'll see final outline on next steps and challenges that lie ahead. So Nestlé, Nestlé is a huge company, pretty much everywhere in the world. The number of sales on a daily basis is just huge, over 90 billion in 2018. We have more than 300,000 employees, more than 400 factories, more than 2,000 brands, and a figure that I really like to mention sometimes so that you will get an idea is like more than 1 billion Nestle products are sold on a daily basis. Just for you to have some fun, you can just see that we are pretty much everywhere. Then the most typical brands, probably you recognize most of them, like Nespresso or Nescafe or Nesquik or Purina, and maybe you find some others that you didn't know were actually from Nestle, but they are. Okay, so the Security Operations Center, what is it, what it does, and what do I do there? The Security Operations Center, or SOC for a faster reference, is a team that is responsible 24/7 for taking care of all the security-related incidents that are happening all over Nestlé. And in the SOC in particular where I work, we are divided in a few different blocks. We could say 4 of them, as you can see outlined below. On the very right, we can see that we have a block dedicated to vulnerability management, which means that we need to take care of systems that are kind of out of date and with well-known software vulnerabilities that could be exploited by external bad actors. Then we also have threat intel, which is all kind of feeds that we can use that have been previously used with other companies, or that is well known by the community, that are malicious indicators of some kind of security issues. Then we have this security monitoring part of the team, which is where the data science team that I lead is located, what we call advanced analytics, where we take care of monitoring all the logs and building smart systems to actually flag anomalous events. And these all 3 blocks just feed information into another final block of the SOC, which is incident response, which takes care of all this input and, let's say, logs all the incidents and routes them through the security analyst that is 24/7, is a team of 24/7 service that is able to take care of all the tickets that are continuously open, right? So why is cybersecurity so important nowadays, and why should I care? Well, I'm just putting here a few numbers, but I'm pretty sure that nearly all of you heard all over the news that on a daily basis, big companies are being tackled by cyber attacks. Just a brief comparison for the last few years. The average number of security breaches that are happening in different companies has risen dramatically, like nearly 67% in the last 5 years, and more than 10 just during the last year, and that translates into, in terms of millions of dollars, an increase of more than 70%. Funny thing is that even though you might think this was only focused to companies with like banking or even software, as you can see on the right side, this is pretty much scattered all over different verticals, going from consumer goods to energy and travel and all kind of services that are actually exposed to the internet. So everyone is exposed, and yes, you should care. Okay, so how do we deal with phishing using deep learning here? Well, the solution overview is quite straightforward. The focus here is to actually monitor dangerous URLs out of emails. Okay, so the idea is that we want to identify login pages that are trying to look like legitimate sites, right? Normally within a company we have the default, let's say, service provider that we use for signing in, like Microsoft or G Suite from Google or whatever it is, as you can see on the right side. So as employees, we do trust when we see that landing page, we do trust that that is something reliable. The thing is that phishers exploit that vulnerability to make you trust it and actually input your credentials when what is behind, what is really behind, has nothing to do with the legitimate service that you think. Okay, so the workflow is quite simple. You get these URLs that go into the data lake, which is the storage that we use on the backend. And then we filter out some noise, like we don't want to receive any alerts related to domains that we know for sure are belong to Nestlé, and we don't want to have that kind of noise. I don't care when someone logs into Outlook, let's say. But what we want really is based on a set of reference images, which are, as you can see on the right, like Office 365 login. What we'll do is after all the filter on the whitelist, we'll run through some deep learning algorithm that will show later how it works for filtering out of those final URLs which of them are actually showing to the user landing pages that are extremely similar to those logins that we trust. Okay. So now, after this brief introduction, I will give the pointer to Fran, who will introduce you into the infrastructure that is behind it.
Thanks, Ignasi. Now we are going to talk about the architecture of Fish Assassin, the name that we gave to the solution. As you can check in the diagram, in the center of the architecture, we use Apache Airflow for orchestrating all the pipelines. So the most important Airflow pipeline is responsible for the detection of possible threats. The main input of this pipeline is a feed of URLs that we need to estimate if they represent a phishing attack or not. Other inputs in the pipeline are public and private threat interfaces similar to FishTank, OpenFish, etc. The main pipeline applies to every URL in the feed many machine learning models to figure out which threats are real or not. So the machine learning models use different features of the threat. For example, there is one model that checks threat patterns in the URL, and another one checks the similarity of authenticated sites, like the Microsoft login, against the URL using web screenshots. In the end, the result of this workflow is a phishing score for each possible threat. All processed threats, scores, and related files as screenshots, HTML files, CSV files, etc., are stored in Azure Data Lake. And the threats with an score over a certain threshold are reported using Event Hub in order to be checked by the SOC team. In the following slide, we can check that PhishAssassin is hosted in the Microsoft Azure cloud. We also use Azure DevOps as source code repository and for CI/CD tasks. So the release pipeline is being used for deploying new environments or updating them. Airflow is deployed using Azure Kubernetes services, using the standard Helm chart from GitHub. Airflow Docker image is customized, so including some solution dependencies like R and Google Chrome for saving web screenshots. This customized Docker image is stored in an Azure container registry. The source code, mainly Airflow DAX, is deployed in the Azure Store File, which is mounted in the pods running in AKS. The result from executing the workflow, CSV files, PNG files, etc., is stored in the Azure Data Lake. The main workflow pipeline can be broken down into many different tasks. For example, the first task collects the URLs to be analyzed. Then we make a first triage by basically doing a Python get URL request and analyzing the response, mainly the HTTP status and the HTML body. After that, the following triage is based on the dynamic whitelist. This whitelist is managed by the solution itself. So the dynamic whitelist is an intelligent cache that allows to filter URLs which have been already processed, but the expiration policy is especially customized for the phishing scenario. Next, we make a web screen capture of the website URL, and also we save the HTML body. This part of the workflow is very important because most of the times phishing websites are only online for a short period of time, between 12 and 48 hours. So we can collect even more information about the threats that other threat intel feeds. Finally, we apply different machine learning models and combine all the results in one dataset, which is stored in the data lake. If the threat score exceeds a certain threshold, the threat is sent to the SOC team in order to be manually reviewed. So we described before the main workflow, but there are also another support pipelines which are dedicated to data ingestion, threat intel feeds, reporting, and managing the dynamic whitelist. All these pipelines have been developed using Python and open source libraries. The main libraries are Airflow for orchestration, Selenium and Google Chrome for web screenshots, Fast.ai for machine learning models, Azure Data Lake Storage for storing the information, and PyTest for unit and integration testing. Now I'm going to briefly show some Airflow features which prove to be very helpful in our development. For example, monitoring the solution is an easy task using the tree view. So you can check latest task execution statuses and clearly check succeed and fail tasks. In the same place where you review the task, you can also have access to the logs associated to the execution of each task. This is different to other solutions where you have the UI to review the executions, but you need to check somewhere else the corresponding logs. Using the same UI, you can also trigger the execution of any pipeline or task. Finally, the Gantt diagrams are also very useful. In some cases, we use these diagrams to drive off our backlog, and we prioritize further improvements in the longer tasks. And now back to you, Ignasi. Thank you.
So thank you, Fran, for your explanation. So now I'm going to proceed with the initial attempts that we had on how to tackle this problem. So first approach, the most naive, I would say, is just comparing pixel to pixel. The incoming image that we want to know if it looks like a reference image that we want to find, right? So how does it work? Well, as you can see on the slide, basically we just find like we compare the first pixel to the first pixel on the reference image, the second with the second, the third with the third, and we keep going. And as you can see, like on the right side, the comparison result would be like these red squares would be the actual differences, right? So you might think that this is a good approach, and we do have there are all kinds of metrics. I just listed some of them below on the slide, like mean absolute error. You can use squared errors. You can even use like not a binary comparison, but use some kind of fuzzy threshold so that it's able to deal with a really small difference between the two pixels. But even though we did try with many of the combinations, it did work for some, but for most cases, as I'm showing you on the right, there are so many little differences. Like you can see here, for example, it's not uncommon to find these two login pages. One of them just asking you straight for a password, like directly, and then the other one is showing you just to sign in with two different text boxes. And this approach would just tell you that for any of those new images that you're trying to compare with these two, they don't really match because the differences are too high. So we had to change the scope and the way to work. So the second approach that we took was actually to use pre-trained neural network. So what is it exactly? Basically, what we use this for is to actually take any new input image that we want to compare with our reference images. We want to transform it into something that summarizes how it looks like in a lower level, that is more resilient to minor changes, as we just saw in the previous slide. And what we do is, out of this schema that I'm showing at the very low end, which is the schema for a ResNet, we just take a certain part of the network that will just do that summarization. So how does it work in general? So I don't know if you heard of it, but there is this well-known data set called ImageNet that has over 1 million images from the real world with over 20,000 different categories, ranging from animals to cars to any kind of object that you can think of, and they all have a classification, right? So then there is this approach, this deep learning neural network by Microsoft called ResNet, that I will not go into detail right now because of the time that we have. But basically it keeps using several layers of convolutions in order to keep learning abstractions out of the input image that will actually be able to, by putting them together, all kind of shapes and combinations of them, will actually be able to tell finally if they are one object or the other, right? For example, we could say that a given image is a cat, is a car, a house, or whatever. But I did say that we want to use this for login pages, right? So what we do is what you can see here after the last layer that I just outlined it in this red circle. Instead of relying on the final classification, what we do is we go back to the last convolution, which is this last bit, and then what we do is to take all this information compressed in a single dimension, so that we can talk now about an image embedding. So we go from an image to an array of multiple numbers that will be just describing how the network understands that image looks like. Okay. So, but what do we do with that super large vector? How is it useful to actually find the phishing that we're looking for? Well, there's this similarity mechanism, probably you all heard of it, which is the cosine similarity, that is able to just tell how far or how close two objects are in an n-dimensional space. In this case, the dimension will be as large as it will be based on the network that I just explained, right? So how does it look like? Well, as you can see on the example below, while these two images that are A and Q are close to one another because they do have similar objects. Look closely and you will see that they are not the same. There is one missing item in Q that is in A. And then another image that has nothing to do with them, like a landscape, is far. Let's say it's farther away in terms of the cosine similarity. So that's what we use to actually find phishing. Did it work? Well, not really. What happened here is that, well, login pages are not really good representations of the real world. It's, let's say, a virtual combination of different items that might be related to the real world or not really. So we are not really finding only the logins that we want to find. What we are finding is something like this, just logins indeed, but they have nothing to do with the ones that we want. Basically, the network is not able to extrapolate the information that we want to find exactly those login pages. So what did we do? So the next step for what is finally now the final solution is to go for deep learning, transfer learning. So what is transfer learning? Transfer learning is quite a heavily used technique to, let's say, translate some knowledge from a pre-trained network, as I just explained, from ResNet, that was used to classify objects from the real world, into your own problem. So what is our problem? Our problem is logging versus no logging. So what we did is we go from the network on the upper side, which is like the ResNet I mentioned before, that will just tell you if a picture is a cat or a car, to the one at the very bottom. So we change the input and we freeze part of the network, as you can see here with the blue lock. But we completely relearn what is the last layer of the network, which is the fully connected normally, so that the neural network will just relearn how all the abstractions that were coming from this pre-trained network are actually useful for the particular class that we want, right? So after this, the embeddings that we use on the second attempt were actually recomputed so that they are able to tell apart actually the images that we want. And what was the solution after this? Well, as you can imagine, as it's called final solution, it did work. So what we get is on the left side, we would get all kind of let's say random URLs that people is accessing, versus all the login pages that are, let's say, of interest. Okay, so in this case, what we would have is everything that goes after this white noise filtering that I mentioned before, like filtering out Microsoft.com, Azure.com, Outlook.com. We'd have these images that look extremely alike, like Office 365 login, but they are definitely not regularly used or accessed by Nestlé employees. Okay, so this system has been in production now for a few months already, and I can tell you that the performance is being well above 90%, meaning that 9 out of 10 predictions are really phishing. So the intersection between the image recognition itself and a proper, let's say, whitelisting of well-known domains, not commonly accessed by employees, this intersection is really quite often about phishing, right? And that would be the solution. And well, just before finalizing, I wouldn't like you to go to finish this presentation with the feeling that it's all kind of solved. So let's just give you some thoughts on what's coming next after this. So deep learning is definitely useful. And for sure it can be extremely, it has extreme potential to help security operations center to deliver more and find more threats. But we do have 3 critical points that are not particular to this problem, but it affects this product as well. The first one being model drift. So what is model drift? Basically, all machine learning or deep learning models, they just learn from what is called a training set, right? In our case, login versus no login. And they just assume that all the images that they will receive come from this fair distribution, and that no one will actually change that incoming distribution. Problem is that that's not exactly like this. So if the nature of the incoming images just changes, the performance of the model will just drop dramatically. So it's really important to monitor every single drop in performance of models in production and retrain if needed. Otherwise, any machine learning solution is not really that useful. Another important issue that is still not that, I would say, well known to the community is adversarial machine learning. This is a very critical one, and it basically means that that, for example, for our case, we train a classifier that is able to tell apart images of interest. Okay. The thing is that there are the abstractions that neural networks are doing are not that strong, in the sense that they don't really understand the image. They're just making certain abstractions. So if the proper noise is added into the image, there are techniques that are already quite mature that are able to actually trick the model into falsely classifying a positive class into a negative one. For example, this Office 365 login, let's just say that an adversarial machine learning system could just generate the same image, but with some strategically changed pixels that would actually make the model think that this is not an image of interest, so it would be just a false negative that we would never see. So it's a really important topic. And finally, an even less discussed topic, but it's coming as AI or deep learning is moving all over the place in our communities for everything ranging from security to health, for example, is the complexity of the models that we use. The ResNet model that I just explained is extremely complex. It has just millions and billions of parameters, and definitely we're not that capable of reasoning about it. So what it means is that we just trust the outcome. In case of images, it's kind of obvious because we can just see the image and understand what happened. But in case of health-related applications, this is not that simple. Or in case of some kind of intrusion, it's not that easy either. We just have to rely on the model, and we should understand it better. So this will become an increasingly complex issue as we move forward with all this kind of AI-based applications. And well, that would be all. I hope you enjoyed the talk, and please feel free to ask any questions if you want.